Hi everyone. So this video is going to be a screencast solution of today's Leetcode problem of the day, which is design graph with shortest path calculator. The name is pretty big and the problem is hard labeled, but let us just see what the problem says. So it says that we have been given a directed graph that consists of n nodes numbered from 0 to n minus 1. Okay. Mm, the edges of the graph has been represented. Okay. So we have to initialize the graph, we have to add an edge, and we have to find the shortest path. There are three functions that we have here. Functions are self-explanatory. Hundred. So the very first thing when you see shortest path, it should be BFS, right? Will BFS work here? So this should be our first question. Uh, we have at most, like, we have 100 nodes. So in any case, even if we add edges, the maximum number of edges can be 100 into 99, that is 9900, right? Now a single BFS will cost V plus E time, right? But since the edges are also weighted, it should be like with the help of a priority queue. Should be log V plus E. Well, that means there would be a factor of log as well. So the value of V plus E is 10,000, right? And log 10,000 is roughly O divided by log 2, that is 13. So there will be a constant factor of 13, 14 as well. So 14 into 10,000 will be the cost of one single call to this particular shortest path function, right? Now if we have 100 calls, the overall complexity is turning out to be 14 into 10 to the power 6. That is acceptable, I believe. Like this much can be done if I have not made any. If I have not made any calculation errors. So let's just try this thing. So we have a vector. So we want to have it here. Let's just create it of size 101, right? And we have the edges. So for auto I in edges, now this shouldn't be like this. It can be a pair of integers, right? Now let's say this is x is equals to I0, the item y is equals to I1, and the weight is equals to I2, right? Now since this is a directed edge, edges, oh sorry, graph of x dot place back. So this is the node and this is the edge, right? Whenever I want to add an edge, so again I can calculate both of the things, all of the things, edges x, y, and weight. So weight will be equals to edges of 2, right? So g of x dot in place back y and w, right? So these are all the things that we need. So let me just compile this first, and I just want to check whether there is a compilation error or not because of this global declaration. Okay, so expected parameter declarator. have we written everything correctly? So the number of these signs is correct, I believe. Okay, acha, one more thing that I would want to do is, and I just make it global. So I can do it like this. Okay, so this works. Now I just want to find the shortest path. That means like my upper part is correct, there is no compilation error. For finding the shortest path, I can have a distance array of initially, let's say all of them are infinity. Now I would also want to have a priority queue. So normally what we do in Dijkstra's algorithm is we have a priority queue. So this is going to have pair of integers. So the first part of this pair is going to denote the current distance that we have traveled till now, and the second part will be the exact node for which we have traveled that much distance. I also need to pass a pair integers, since by default priority queue is max heap, right, and I want the value in front to be as small as possible. So I would want to take it negative. Let me just check one more thing. What is the weight, values of weight? Have they given this value? Yeah, so the weights will be a positive only. Now I can have the third part. This is just a boilerplate code. So for writing priority queue, parent comma int, and like this. One more for the first. So I can just push the node 1, right? I need to write the distance first and then node 1 like this, right? Now I can also mark the distance of node 1 as 0, and while my PQ is not empty, PQ.empty, I can get, let's say, the current distance and the current node. So this will be in PQ.top, and I can just pop the element. Now I have the current distance and current node with me. I want to visit all the nodes for auto, let's say next in graph of node. Now I can find out the weight as well as the child from this next. So it is going to be, first we had child, then we had weight. It is from this, if current distance plus weight is less than distance of child, right, then I would want to update the distance of child is equals to current distance plus weight, and I also want to push it into the queue, distance of child comma child, right. So this is how we normally do priority queues. Okay, so at the end what I would want to do is return distance of node 2, right. So if this is equals to 1e9, that means we have not been able to reach this node, so I'm just going to return -1, otherwise I'm just going to return its distance. So this is correct, like this should be logically correct, but I am just worried about the time complexity if I have not made my analysis wrong. So I'm just trying to submit this. Let's see. So it is accepted, that's good. So yeah, this code is correct, and I would say you just need to observe how the time complexity plays out. So for this problem, it was roughly 10 raised power 7, and I thought it should work, and it did. So you see, this is my first attempt only. I did not solve this problem earlier, and that is the purpose of these screencast videos, essentially to like to convey the idea to you guys how I am thinking about the problem, and if this did not work, we could have thought of some other method. but it does, and looks like a simple Dijkstra for all the calls will work, right? So that is it for this video. I hope that you guys were able to understand the solution, and I'll also be uploading similar videos for geeks and other Leetcode problem days as well. So in case you're interested, definitely check them out. And let me just give you an idea once more. So I believe this is just Dijkstra, so that you can figure out on your own. But I'll just try to give you one idea of the time complexity, why I moved ahead with this particular method. So let's say there are 100 nodes, right? There are 100 nodes, and no matter how many calls are made to this add edge function, right? In the worst case, let's say we have n into n minus 1 edges, right? This is the number of edges that I can have. Let's just ignore that these calls will be made to add edge function. We are just going to consider the absolute worst case, right? So in that case, 100 into 99 edges will be there. So this will be 9900, right? Now these many edges are there and 100 nodes are there. So the value of v plus e, which is the complexity of a simple BFS, it is going to be 10,000 or 10 raised power 4, right? Now since we are using a priority queue here, it's a Dijkstra algorithm for weighted edges. So we are using a priority queue. Let's just introduce a log n factor to it as well. So log 10 raised power 4. This is in base 2. So I can write it as 10 raised power 4 into 4 divided by log. If I write it in base 10, 10 raised power 2, right? So I just converted this into base 10. So this was actually log 10 raised power 4 like this. So this came out to be 4. So 4 upon log 2 will be our value. Now I calculated this by 4 upon log 2. So this is roughly 13 point something, this value. I considered it to be 14. So it should be 14 into 10 raised power 4 for one single DFS or for one single BFS or finding the shortest path. Now they say at most 100 calls will be made to this shortest path function, right? So this will be called 100 times. So this was roughly 14 into 10 raised power 6, that is 1.4 into 10 raised power 7. So this was the rough time complexity in the worst case, in the absolute worst case, right? So I believe this was it about this problem. When I saw this particular thing, I thought that brute force might work, and it did. So you can solve this problem now easily with the help of simple Dijkstra algorithm. I'm just quickly going through my code. I just created a global graph vector, and the first part of this pair is going to denote the node, and the second part is going to denote the weight, right? So this line means x is connected to y and there is a weight of w, right? Similarly, when I add an edge, I do the exact same thing. X is connected to y and the weight is w. Now I need to find the shortest path between node 1 and node 2, right? So I create a priority queue. By default, priority queue is max heap, so the maximum element is present at the top, but I wanted the minimum distance to be present at the front. So I include this part. This is just a boilerplate code, right? Now when I do this, I just push the smallest node, that is the node 1 with the distance 0. So the first part is actually denoting the distance, current distance that I have traveled, and I have traveled that much distance for this particular node, right? And I have also marked it in the distance vector. Now I'm just going to make a while loop while my priority queue is not empty. I'm just taking the front of the top of the priority queue, which is the current distance, which will give me the current distance and the node. So that basically means to reach this particular node from node 1, I have traveled this CD distance, right? And this is the minimum distance that is possible. Now I'm just going to traverse through the adjacency list of this particular node, and obviously, like you must have seen it here, what we store in the adjacency list, the first part is the child and the second part is the weight. So if current distance plus the weight I have to spend from moving to this node to the next node is less than the distance of the child, then I update my distance of the child and push this new child into my priority queue. So obviously the first part will be the distance travel and the second part will be the node itself. Now at the end, if the distance of node 2 is not infinity, that means I can return -1, and that means I can return the distance of the node. Otherwise, if it is equal to infinity, I have to return -1 because that node is not reachable. So that was it for today. I hope that you guys were able to understand this, and till the next video drops, keep coding, stay safe, bye bye, and don't forget to drop a like and comment on this video, because your engagement with this video really helps the YouTube algorithm to understand that this video was actually helpful for you and it will be able to reach much more people like you who want to keep solving new problems. So till then, bye bye.